So number 4 on page 74, where it starts off with 1, -2, 3, -4, 5. And then yep. So number 4 is 0, 2, 6, 12, 20. This one here. Yep. Huh? We can look at that in a minute. So what did we do to go from 0 to 2? How about 2 to 6? 6 to 12? So the next number would be? So each number is increasing by 2 more than the previous, or something along those lines. And then I think there was a question on 15. 15 and 13. 13, 14, 15. The product of two positive numbers is always greater than either number. So 13, the product of two numbers is always greater than either number. So two positive numbers. 2 and? Because 2 times 1 is 2 greater than 2? Because I don't think you had to do 14. Because I think it said 13 through... Okay. Oh, yeah. Sorry. Yes, it was 14 was 1. Let's look at 15. So we have two angles are supplementary of each other. Then one of the angles must be acute. So what are we saying? The two angles have to add together to be what? 180. So what two numbers that we can add together to be 180? 90 plus 90 is 90 or 90 acute. They could be two right angles. For 14, the hint I would give you is you might try something less than 1. Because any number greater than 1 will work just fine. Any number less than 1 I think would work. I think, is that London? You had something along those lines? Or the numbers that you tried were less than 1? Yeah. So try numbers less than 1, that might work for 14. Yeah, try either one of those. Because it might work when you plug that in for n, that it will not be true. It'll be a counterexample. So let's look at the note sheets for today. 2.22. 2.22. Now, what we're looking at today is deductive reasoning. Now, inductive reasoning, we made a statement based off of what? Observations, what we saw, yes? Because we saw a pattern and we made a statement about it. So deductive reasoning is not going to be based off patterns. It's based off of what? Facts. You're welcome. Deductive reasoning is going to be using facts, definitions, accepted properties, and the laws of logic. So our law of detachment or the law of syllogism to show that something's true. So we're using facts, we're using properties. We are actually using something that we know to be true to make the statement of what's going on and what is occurring. Now, we do have two laws of logic. One of them is the law of detachment. Now, the law of detachment states if the hypothesis of a conditional statement is true, then the conclusion is true as well. If we can say that the hypothesis is true, then the conclusion must follow. Now, the law of syllogism is really stating if we have two true statements, if P, then Q, and we have if Q, then R, I have two statements that are both true, and the hypothesis of one and the conclusion of the other match, are the same, here. Let's get a highlighter. Because the conclusion and the hypothesis are the same, we can make a new statement from the other two parts. If P, then R. And again, once we do a few examples of these, they'll make a little more sense. Well, I'm going to write in. So let's look at the first one here, using the law of detachment. The conditional statement they give us, if two segments have the same length, then they are congruent. If two segments have the same length, then they are congruent. You know that BC equals XY. Using the law of detachment, what statement can you make? Well, BC equals XY. That tells me that the length of BC is equal to the length of XY. We don't know what they are, but we do know that they are equal. They have the same length, yes? What's the hypothesis of our statement? If two segments have the same length. Can we say that's true with BC and XY? Well, yes, they told us that they have the same length. So according to the law of detachment, because the hypothesis is true, they told us this, it is true, it means the conclusion must also be true. That they are, so we can say that BC, line segment BC, is congruent to line segment XY. Or we could say, I mean, if we wanted to write out, I mean, that's really it. I mean, we could put it into words that line segment BC is congruent to line segment XY. But really, we're saying that the two are congruent. Because it satisfied the hypothesis of the statement, the conclusion has to be true. Questions on this here? Okay, before you freak out, this isn't on your note sheet. I wanted to do some more examples of this here, and I already printed them out. So instead of having Eric unstaple and put a page or two in and then restaple it back for you, we can just look at these here. So our conditional statement, if a figure is a square, then it is a rectangle. So if a figure is a square, then it is a rectangle. You know that quadrilateral ABCD is a square. Well, does that satisfy the hypothesis? Because what does it tell us? ABCD is a, if a figure is a, so that part follows up. That lines up with the hypothesis, yes? So it says the hypothesis is true, therefore the conclusion must also be true. So that means that A, B, C, D is a what? Rectangle. Because the conclusion is, then it is a rectangle. Well, it told us ABCD is a square, so by our conditional statement, ABCD is also a rectangle. And that's it. Questions on this here? Let's look at one more. If today is payday, then you will get paid. If you got paid today, what can we say about this here? Is this making the hypothesis true? Right. Yeah, it's a little funky, but this is talking about the conclusion, isn't it? This one's not in the note sheets. So this is talking about the conclusion, yes? Can we say anything about it? Well, no, because, I mean, you could have gotten paid in some other way. Because the only way that we can use the law of detachment is if the statement they give us, or the information they give us, makes the hypothesis true. Because whatever they give us makes the hypothesis true, then the conclusion must also be true. But if they give us information about the conclusion, we can't say anything about the hypothesis. It doesn't go the other way. For us to be able to use the law of detachment, whatever information they give us has to match up with the hypothesis of the statement. Otherwise, we can't say anything about this here. Questions on this here? Okay. Now we're going to look at using the law of syllogism. Now this is in your note sheet because it's on the back of the first page. If possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. X squared is greater than 25, then x squared is greater than 20. Well, yes. If a number is greater than 25, it's also going to be greater than 20. That is a true statement. If x is greater than 5, then x squared is greater than 25. Well, 5 squared is 25. So if a number is greater than 5, its square is going to be greater than 25. These are two true statements. Now, one of the big things I said when we looked at this here to start with the law of syllogism, is that the hypothesis of one and the conclusion of the other must match up for us to be able to use this. So, is one part of this match up for both of them? Because we have, if x is squared is greater than 25, then x squared is greater than 25. Those do match up. We do have a hypothesis and conclusion that match. Yes? Then we can use the law of syllogism by connecting the other two. Now, which one's going to go first? If x is greater than 5, then what? Then that's it. If a hypothesis of one matches the conclusion of the other in the two statements, we can use it, and we take the other two and put them together. And the if is always going to go first. That's it. Questions on this here? Are you ready for the next one? If possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. If a polygon is regular, then all angles in the interior of the polygon are congruent. If a polygon is regular, then all its sides are congruent. Well, these are two true statements, and we will actually delve into regular polygons because all the interior angles will be congruent, and all their sides will be congruent. Now, do we have two statements that line up? A polygon is regular and a polygon is regular, yes? Is one of them in the hypothesis and the other in the conclusion? No, they're both in the hypothesis, yes? So can we use this law? No. Because we can say not possible. We can't use the law of detachment to put these together. or not law of detachment, law of syllogism to actually make a new statement from these two. So it's just not possible. Questions on this here? Very good. Okay. Now this next problem here, you probably noticed that the problem on top of your note sheets and in the middle are the exact same thing. We're going to look at this in two different ways. We're going to look once at looking at this in an inductive way, and then we're going to look at it in a deductive way. So if we look at this using induction, well, induction is using examples, trying to show a pattern exists. Because if I can show a pattern, then I can make a statement. What conclusion can you make about the product of an even integer and any other integer? I'll give you an even integer. And someone else just give me another integer. 3. 2 times 3 is? Yeah. Because it's just asking for an even and a other integer. Yeah, we can do even and even. So what would that be? 2 times 4 is? 2 times 4 or 4 times 2?
Okay, I just keep on hearing 3.
Oh, okay, yeah, no. Because we could do 3 and 8. And 3 times 8?
24.
Well, let's just do, say, negative 2 and 5. Negative 10. What is in common with all of these numbers here? They're all even, yes? Because the product of an even integer of an even integer and any other integer is always even. Yeah, I put product and of really close together. And that's it. So that would be using inductive reasoning to show that this is true. Questions on this here before we look at deductive? Yes, sir.
Okay, so you said so it has.
What?
How could you always be? Don't you like times would be odd?
Okay, like? Let's look at the deductive, and it'll actually make sense here. So let n and m each be any integer. Use deductive reasoning to show that this conjecture is true. So n and m are really are just integers, yes? And we want one of them to be even, no matter what they are, yes? So the easiest way to make one of these even is say if I take 2 times n, yes? So 2n is even. Because 2 times any number, it will be even. It's divisible by 2. So this is even. So 2n times n, 2n times m, if we take the product of it. This is the same as saying 2 times nm. Well, nm is just going to give us another integer, yes? Well, if it's 2 times an integer, it is still going to be even. because anything times 2 is going to be even. 2 is an even number. So therefore, all numbers that an even and an odd or any other integer multiplied together will give us an even integer. Now, so 2n is an even integer because integers multiplied by 2 is even. 2nm represents the product of an even integer 2m and any other integer m. 2nm is the product of 2 and an integer nm, so 2nm is even. And this here is more along the lines of what a mathematical proof, an actual proof would look like. We would do this here, talking about it in terms of any number, not a specific case. Questions on this here? You're not going to be asked to do something like this here because it does take a while to get in that mindset of setting those up and figuring those out. Decide whether inductive or deductive reasoning is used to get to the conclusion, and explain. So let's look at this here. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up into the air, it will return to the ground. Is this inductive or deductive reasoning? Why would we say inductive? It's a pattern, isn't it? Because each time she kicks it up in the air, what's happening? She's kicking the ball up in the air and it's coming back to the ground, yes? We don't have any definitions of gravity or how that's affecting the ball or what she's doing. It's just each time she does it, it comes back. It is a pattern, or we can say observation. It's a pattern or observation. Questions on this here? We're ready to look at the next one. All reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. Because we are using what? What are we using? Facts, definitions. Because it is a fact that all cold-blooded, or reptiles are all cold-blooded. That's just a fact. And it is also a fact that parrots are not cold-blooded. No. Because by definition, reptiles are cold-blooded, yes? By definition, parrots are not cold-blooded, so Sue's pet parrot, by definition, is not a reptile. So it's deductive because we're just using the facts of what a reptile and a parrot are. Questions on this here? That's it. That is all we're doing for today. So y'all can use the rest of your time to work on